Hi everyone, so today's topic is going to be linear regression. In the last lecture we learned about scatter plots and correlations, and you learned about how to calculate correlation in the class. But we need more than correlation, because correlation only tells us about the strength of a linear relationship. Because it's a linear relationship, we can actually express the relationship with a line. But correlation doesn't tell us what the line is. We need a linear model. So today we are going to learn about simple regression. That's a mathematical model for describing a linear relationship between an explanatory variable x and a response variable y. It is a straight line that describes how y changes with x, and it can be used to predict the value of y for a given value of x, predicting y based on x. So let's say we draw a approximately good line and x, and you can draw the line to the estimated line and then get the predicted value. But the actual value was here. That is observed value. And there is a difference between the predicted value with the observed value. We usually use hat for predicted value. So to find the line of best fit, we can use the sum of the squared residuals, because we don't need to take into account the sign of the residual, so we are using squared. That is basically distance, and we want to find the line that makes the distance between the observed value and predicted values is smallest. And we can express that with this mathematical expression. So arg mean and sum of the squared residual y minus predicted value and square. So that is basically the distance and squared residuals, and finding a parameter that minimizes this value is the least squares line. So we previously learned about deviation, that is y minus y bar, is mean, and how different they are. So this is just how the y value changes from the mean of y, but this is the predicted value with the regression line. So if I say this mean value as a simplest model that I can think, and y hat is based on more elaborated models like linear model. We can write the linear model in this way: y hat equals b0 plus b1 times x. Here b is coefficients, and we usually read this as a beta, and beta 1 is a slope, the slope of the line, and the intercept is where the line meets with the y-axis. And actually slope can be calculated using this equation. So the correlation times the standard deviation of y and standard deviation of x, that divided by standard deviation of x. Yeah, here the correlation do not have units, but slopes have units. Therefore we are multiply r with sy, so standard deviation of y, and divide that with standard deviation of x. Because correlation use the standard deviation as a ruler, because of that we are doing this calculation. And we can calculate the intercept using the mean, because the line will pass every time the mean of x and y. We can replace these values x and y with mean of y and x, and then we can calculate the b0. Okay, let's look at the example data from a sleep study. If you have more sleep deprivation, and then you can have more errors. So these numbers are errors you made, and these numbers are hours without sleep, so sleep deprivation. So if we calculate the x bar, the mean of x, that is 16, and standard deviation of x, that is 6.32, and y bar equals 10.6, and standard deviation of y equals 3.05. If we calculate the correlation, that's 0.985. That's really high correlation. And based on these values, we can calculate B1. So that is slope. So B1, 0.475. And using the mean of x and mean of y, we can calculate the B0. And then you can get 3. So the least squares regression line is this, 3 plus 0.475x. So this line has some properties. In general, the slope has units, so y units per x units. So here, errors per hour without sleep. The y-intercept is not always meaningful because the x value, x equals 0, is not always meaningful. The least squares regression line always passes through the point x bar and y bar. That's why we can calculate B0 with x bar and y bar. If both the variables are standardized, the regression line is given by this. Because the units are 1. So B1 equals just R. Okay? And Zx bar equals 0 and Zy bar equals 0, and therefore B0 equals 0. I just said that residual equals observed value minus predicted value. In least square regression, the sum of the residuals is always 0, and the residuals are the variation in the data that has not been modeled. Therefore, by adding error residual term, we can remove this hat. So y equals B0 plus B1x plus error, E. A residual plot is a scatter plot of the residuals against x or y hat. And we are gonna examine the residual plot soon. But when studying the residual plot, we hope to see no pattern. I just wrote a couple of lines in MATLAB to see that's actually true. That given that we got this regression equation, we can calculate the residuals by subtracting this y hat from y. Summation of residuals, it is almost 0. And when I made a scatter plot with x, real x value, and y-axis will be residuals. So this is the plot that I draw. So this is residuals and this is x here. And this plot should be the most boring scatter plot you ever seen. So there should be no pattern. Shouldn't have any interesting features, direction or shape. Should stretch horizontally with about same amount of scatter throughout. So the scatter should be similar as the x increases. So no bends, no outliers. So SE is standard deviation of residuals. And that tells us how much the points spread around the regression line. So standard deviation of E equals the sum of E square and divide that by n minus 2 and square root of that. Why n minus 2? We will talk about this in later lectures. There were some assumptions for correlation. A quantitative variable condition and straight enough condition and low outlier condition. And in regression, there is one more condition. That is, does the plot thicken condition. That means the the residual plot should have equal variance. That means the spread around the line should not increase as x or the predicted values increase. So we can actually investigate this assumption by looking at the residual plot. Data are thickened as the x increases. The residual plot will be thickened. We'll have this type of a funnel shape. That's not good. So when we examine the residual plots, there should not be any bends. That's straight enough condition. And there should not be any outlier. That is outlier condition. There should be no changes in the spread. That is does the plot thicken condition. So we can do very many things by examining residual plots. So residual plots are very important. So how do we know the regression model I got is good or not? We need a method to assess how good my regression model is, and we are commonly use R-Square. So the correlation provides information about strength and direction, and to evaluate how well our regression model does, actually the direction is not important that much. So we really care about strength. So we made our R-Square that ranges between 0 and 1. So we remove the minus values, but sometimes R-Square can be minus if the model is not linear. But in the linear model, it always goes between 0 and 1. And that tells us the fraction of the data's variation accounted for by the model. And the basic idea of R-Square is subtracting remaining variance from the total variance, and therefore we can get the explained variance, the variance explained by the model. So the denominator should be the total variance, that is the sum of square deviation from the mean. So because the mean is the simplest model that we can get, using the simplest model, this is the total variance of the data. And using the regression model, we can calculate the residuals, and this is the remaining variance. So original variation left in the residuals, right? By subtracting this from 1, we can get the explained variance. So in the linear model, R-Square, larger R-Square, is same with R-Square. How big should R-Square be? It really depends on data type and research field. And what is more important between beta and R-Square? Beta means the relationship between x and y. That tells us about the x unit and y unit, the relationship between those. And R-Square provides us the strength of the relationship. And it really depends on data type and field and research question. Sometimes beta is more important, and sometimes R-Square is more important. So predicting y with x is quite different from predicting x with y, because what we are minimizing when predicting y with x is this. So y minus y hat, right? But what we need to minimize when predicting x with y is totally different equation. So the sum of x minus x hat squared. In this regression model, the B1 should be R, so correlation multiplied by standard deviation of x and over standard deviation of y. So this is quite different from this. But what if we are using standardized value in regression? Basically they are same, because R is a slope. So that's all for today. And there is always the quiz. Find the link in the note. Okay, see you in the class.